Welcome to the Bentley tutorial series for Engineers Without Borders USA. This presentation introduces WaterGEMS and covers the process and purpose of creating a hydraulic model. The available Bentley software for EWB members includes WaterGEMS, which is a state-of-the-art software tool primarily for the use in modeling and analysis of water distribution systems. It is quite powerful yet still very easy to use. When using WaterGEMS, it is important for students and practicing engineers to understand the methodologies behind hydraulic computations. These concepts should be well understood so the model can handle the solution process. The system calculations can be tedious and repetitive, which makes it a task well suited for computer analysis. WaterGEMS provides intuitive access to the tools you need to model complex hydraulic situations. EWB chapters are faced with designing or redesigning water systems in their project communities. The design should begin with data collection and system analysis, which should be completed for the most part before modeling. WaterGEMS is for the hydraulics-focused part of the design. The support of a pipe bridging a river is an example of a non-hydraulic design component, whereas the pipe materials and diameters, internal pressures, and pump definitions are all part of the hydraulic design. The design process consists of calculations, schematic and design drawings, graphs, and reports that describe all of the components in the network. The components can include tanks, reservoirs, pipes, and valves. WaterGEMS is capable of civilizing these tasks for your chapter in a way that is faster, more detailed, less error-prone, more easily documented, and reproducible. Your chapter may consider why you would want to create a hydraulic model. So the model allows for the what-if analysis. It is useful for both designing new systems and analyzing the performance of existing systems through complex calculations that aren't easily done by hand. With the model of your real-life scenario, you can determine what is going on inside of your system. You can test proposed alternatives in the model without having to build a physical version. For a water network, it enables you to evaluate the distribution of pressures and flows inside the network. The design could be tested with a new pipe material or a different size pump, for example. This poster was created and provided courtesy of Lehigh University chapter of Engineers Without Borders. They developed guidelines on why the WaterGEMS model worked for their chapter. These are a few of the advantages they cited for using our program. They could create multiple scenarios and analyze differences in their system behavior, display hydraulic and energy grade lines to visualize the head throughout a system, and plot flow demanded, supplied, and stored over time. That's data that could be used for assessing a tank's suitability for a community's demand, for example. So how does the model work? The user provides network information like pipe properties and demands. Also, sometimes further operation rules are provided for dictating things like the interaction of pumps and storage. The system calculates flows, pressures, hydraulic grade, and more through a system of equations. The water model is demand-driven, so you will be modeling the distribution of flows and pressures in response to demands. The performance of your new or improved system is measured by how well it delivers on its demands. It is important to remember that since the model is a representation of a real-life situation, the better the quality of the provided data, the better the quality of the model. This is well expressed by the modeler's axiom, garbage in, garbage out. We will briefly review the continuity and energy principles because they are at the core of hydraulic calculations and therefore at the core of hydraulic designs. The continuity principle is essentially the principle that mass is conserved. In the case of water distribution system, the mass is water and we are concerned with it entering and leaving our distribution system. It's necessary to consider the system's inflows, outflows, and storage, which could be in pipes or tanks. And given that we make a fundamental assumption that water is an incompressible fluid, the continuity principle also says that volumes are conserved. Another hydraulic consideration is the energy within the system. When the flow in a network is driven by a pump, the designer has some degree of control over how much and where energy is injected into a network. On the other hand, gravity-driven water networks don't have an outside source from which energy is applied. This is the distinguishing characteristic about gravity-fed rural systems, and the challenge there is to effectively manage the conversion of pressure energy. In hydraulic applications, energy values are often converted into units of energy per unit weight, like feet pound per pound, resulting in units of length like feet. These length equivalents give engineers a better feel for the resulting behavior of the system. When the energy is expressed with these length equivalents, it's called head. Energy at any point within a hydraulic system is often expressed in three parts: pressure head, elevation head, and velocity head. Energy can also be added to a system by a pump or removed from the system by friction or other disturbances. These changes in energy are called head gains or head losses. So the energy at the end of the pipe is equal to the energy at the start of the pipe after you subtract the head loss. The hydraulic grade is the sum of the pressure head and the elevation head. In a pressure pipe, the hydraulic grade represents the height to which a water column would rise in a piezometer, which is a tube open to the atmosphere that measures static liquid pressure. When the hydraulic grade is plotted as a profile along the length of a pipe, it is referred to as a hydraulic grade line, or HGL. In general, the more length of a pipe that water flows through, the greater the energy loss, the greater the drop in HGL. Head loss is the difference between points on the hydraulic grade line. The energy grade is the sum of the hydraulic grade and the velocity head. This grade is the height to which a column of water would rise in an instrument called a stagnation tube or a pitot tube. In the image, the piezometer, which shows hydraulic grade, is on the left, and the pitot tube, which shows the energy grade, is on the right. It makes sense that when the water velocity is 0, the energy grade is equal to the hydraulic grade. We've stressed that managing the hydraulic energy within the system is essential, and that includes acknowledging the energy losses and gains. Friction losses are also called major losses and are defined by the friction distributed over the length of the pipe. There are many different equations that approximate the head and friction losses associated with the flow of liquid through a pipe. Commonly used methods include Chezy's equation, which has traditionally been used in sewer system design, but its use is giving way to the Manning's equation. The Manning's equation is used to model open channel flow. It's most frequently used for sewer system calculations, so we won't examine it in depth. The Darcy-Weisbach equation, which is not commonly used in the US, but it is frequently used internationally. For the work of EWB chapters, the engineering standards may be driven by local standards and policy. Luckily for you in WaterGems, it is very easy to try these different friction models. The Hazen-Williams equation is the most widely used in the design and analysis of pressure pipe systems. The Hazen-Williams equation includes a roughness factor, called a C factor, which represents a loss of carrying capacity and is determined by the lining material of the flow channel, which in the water distribution case is the material of the pipe. To give you an idea of C values, 40 is on the low end and would represent an aged pipe with significant scaling on the inside. And a C value of 150 is a very smooth, ideal pipe with very little friction. WaterGems does store C values for any pipe material or age that you designate to a pipe. There are certain assumptions that are used for pressure piping systems that help simplify those general friction loss equations. First, pressure piping is usually circular, so the flow area, wetted perimeter, and hydraulic radius can be directly related to diameter. Pressure piping systems have full flow throughout the length of the pipe, so the friction slope is constant. The energy grade line and hydraulic grade line drop linearly in the direction of flow. Because the flow rate and pipe cross-sectional area are constant, the velocity is also constant. Those are major losses. So for minor losses, they are a localized area of increased turbulence caused by valves, meters, or fittings. In our network modeling world, minor losses are just that, minor. Accounting for all minor losses can be a bit tedious, and their consideration is very often a matter of engineering judgment. Often they're minor enough to be negligible next to major friction losses, and may be ignored during analysis and blended into calibrated roughness. However, a major role of the engineer is to determine which assumptions can be applied. The great thing about the hydraulic model is that they allow engineers to explore the sensitivity of their assumptions. Head gains are achieved from pumps. They add energy to the flow to counteract head losses and hydraulic grade differentials within the system. Pressurized water systems usually have centrifugal pumps. A centrifugal pump is defined by a characteristic curve which relates the pump head to the flow rate. So again, the pump curve relates the head added to the system to the flow rate of water going through the pump. To determine how the pump will be operating in your system, you'll need both a pump curve and a system curve that describes the lift and losses in the system. When the curves are superimposed, the system operating point can be located. A centrifugal pump's characteristic curve is for a fixed motor speed and impeller diameter. However, if you do have a variable speed pump, it can be determined for any speed or diameter. To review, we'll go through some assessment questions. First, Lehigh University cited all but which of the following as reasons for using water gems? Either to create multiple design scenarios, design a pipe bridging over a water crossing, displaying hydraulic and energy grade lines, or plotting flow demanded, supplied, and stored. So if you remember, they did not cite that designing a pipe bridging over a water crossing was an advantage because this is actually an example of a non-hydraulic design parameter that water gems would not deal with. Second, the Hazen-Williams equation is most widely used for which of the following? Either calculating hydraulic grade, the continuity principle, pump energy values, or general friction losses. And it was one of the many equations used for calculating general friction losses. Lastly, water systems with pumps have the ability to add which of the following? Either energy or head gains, minor losses, hydraulic grade lines, or additional water volume. And if you remember in the discussion about head losses and gains, pumps add energy or head gains to a system. This concludes the hydraulic fundamentals tutorial. Thank you for joining us, and please check out the next tutorial.